About the end. Yeah, about the end.
There should be one here. Yeah, do you mind after class if you ask? That's perfectly fine. In fact, because I know James and Morgan have questions about it too.
So that's about the entire. Oh wait, I need another one. I don't know. I'm not gonna share.
Okay.
No, he's got it. Oh, no.
Thank you. You're welcome, sir.
I like taking.
And then I'll assume we'll be here a little bit later, or eventually. So for those of you guys that are in Calc 2, I saw this one. It was some of you guys might have this one for homework or something like that. Anybody remember doing that one? Yep. How many pages did that take you guys? That was horrific.
I think it was page.
No way.
No,
you must have done it wrong.
No, that's
You must have.
That's the one where you have to split it up and then use
And you get like a coast to the 6th down. That's like you get to use the power reducing formula twice on that. Man, I was helping someone in your class, and that problem literally took me about 5 minutes to do, which means it probably would have taken some of you guys like about a half hour.
Oh wow! What are you trying to say?
It's a hard problem.
I got close to it, but I never took up the
Yeah, this one's just hideous.
The problem is when you get the first part wrong and then the next page.
Right. Yeah. I had a sign error because I punched it into mathematics at first, and that's what the 5 minutes took me. Like it took me about 3 minutes to do the problem, and then 2 minutes to find my stupid sign error, which I actually did at the beginning of the problem. Because when I divvied it up and I distributed, and then I used the what was it, the power reducing formula on this animal, I must have distributed something out wrong. Because I was doing it so quickly. What's that?
I hope to never need that again.
Yeah. Well, most of the time what people do is just plug that into Mathematica and get the answer from it. And no, I'm saying that's a difficult problem. I feel bad for you guys. So that's what I'm trying to say. All right. Anyway. Okay. What do we have to do? We have to do induction. And then also what we're going to do is next Monday we're going to do induction again. Okay. So Monday we're going to finish up induction. Yep. And then we will review for our exam. Okay. And then guys, just a reminder about like the assignments and all that stuff, just in case you guys forgot. Assignment number 6 is going to be due on Monday next week. So I think that's the 17th, right guys? And then assignment number 7, that's going to be due on Monday the 24th of October, by the way. Just making sure you guys know the right month for that. And then don't forget, guys, our exam is going to be on next Wednesday. Okay, so exam number 2, Wednesday, October 19th. Okay? All right. And basically, guys, it's going to be all the proof stuff that we've been doing and then some of the sequence and series stuff. Okay? So if you guys have any questions about anything beforehand. Okay.
Is this the test most likely to give you an aneurysm?
Yeah, this is probably the hardest test of the semester. Most of the time, once students make it through this test, they're probably good for the rest of the semester. So, and I have a lot of confidence in almost everyone in here, except if you're wearing a green shirt. Oh, how about that? Oh, just as easy to put an F as just as an A or a B.
That's fine.
Okay. Other questions, guys, I can answer for anybody before we go ahead and get started with everything. Okay.
Did you grade the homework?
I did grade the homework. I posted the grades, didn't I?
Yeah.
Okay, so I'll give those back at the end of class. So, and I need to post the solutions for those, don't I, guys? Okay.
Did you post the solutions for that one?
I did for, I think assignment 4,
Yeah.
and I didn't for assignment 5
I
yet.
meant that last problem that we
didn't do in the notes?
No, can you remind me, can you email me and remind me? There was one problem I did that I
forget
didn't
when I
do.
read.
I know, and then you'll blame me for forgetting too, so. But if somebody would remind me, there's 25 of you and there's one of me, so one person can remind me. Just email me and say, hey Chris, post that last problem, and I'll remember what you need, that's all. Okay, other questions, guys? Okay, so, and I will post all the solutions. I think I just forgot, honestly, so just blame that on me, my bad. Okay. Yeah, we all do, like your parents. So, so I want to talk about mathematical induction. This is going to be the last topic that's going to be on our examination. Basically, guys, mathematical induction is when you can't prove something by utilizing indirect proof, if indirect proof doesn't work, okay? We can use this process called induction, and there's 3 steps to being able to do this. Most of the time we use induction to prove like a series is true, or if we try to prove a formula is true, okay? Not like even and odd, although we could prove using induction for even and odd. We can prove divisibility sometimes, but mostly just for series and sums like that. So we have this thing called a basis step, which is the easy step. You just basically plug in a small number in the domain, see if it works, okay? If you do that, you get at least 3 points out of 15 for the problem, okay? The hard part of the problem is step 3, okay? Step 2, you just basically say if the basis is true, you just assume that it holds true for any small value, okay? And you can't disprove it, okay? Then what you have to do is, mathematical induction says that you can show it true for every case thereafter. In other words, if you can prove it for the case plus 1th case, then the formula must be true, okay? So, basically you just show it true for some small case, you assume it true because you cannot find a counterexample, then you prove it true for every case thereafter. Okay, that's called induction. Okay, sounds like it's a bunch of crop, but it really is one of the most powerful mathematical methods that we're going to utilize. Okay, so mostly today we're going to take a look at series. Next time we're going to take a look at maybe divisibility and then inequalities. Okay, so let's just go ahead and show something that's, and I don't want to say any of these are basic because they're all pretty tough. Okay. But I want to prove the following by mathematical induction. So I want to prove that for any integer n bigger than 1, 3 plus 6 plus 9 plus 12, in other words, if I add up successive multiples of 3, we can summarize it by this formula. Okay? And Art, I think you might have said on Monday, like an arithmetic sequence or series. That's actually what an arithmetic series looks like, the sum of that. Okay? So let's just go ahead and see if the sum of this arithmetic series truly is equal to this. Okay? So here's our proof. All right. Now, whenever we do our proofs, we start with a basis step. Okay? And again, just like we've done for all the other proofs, I'm just going to put in brackets stuff that's not necessary, but it could be helpful when you guys are going back through your notes. All right. The basis says we have to show this true for a small value of n. Okay? So let's just use 2. Okay? Just because I don't like using 1, so I can show you guys what happens with 2. So let's let n equal 2. Okay? Now, 2 means on the left side, I'm going to add up the first 2 terms. Okay? So I'm going to put this in brackets. On the left-hand side, this implies that you add the first 2 terms. Okay? So does that make sense as to what n means on the left-hand side of the series? It just means that we're going to add 3 and 6. If n was 4, we would add 3 plus 6 plus 9 plus 12 on the left side. On the right side, we're just going to use direct substitution. Okay? A lot of students often, well not a lot, but some students often confuse what n means on the left-hand side. So on the left-hand side, we're going to get our first term, and we're going to have our second term, so that's 3 plus 6. On the right-hand side, I'm just going to directly substitute 2 back into the formula. So that's 3 times 2 times 2 plus 1 divided by 2. Okay? So over here, we just use direct substitution. All we have to do now is just do a basic computation, and I think everybody in here can see the left-hand side is 9. The right-hand side is going to be 6 times 3 divided by 2, which is also 9. Okay, so this would be 9 equals 9. Okay, and I'm not good at math, but that seems like it's going to be valid. Okay, so Guys, that's as easy as it gets, right guys? That's not even math. That's just like very, very simplistic substitution arithmetic. All right, if we can do that, we at least get 2 or 3 points for this problem, okay? Now, that's step 1. We've showed it true for the basis step. Step 2, okay? This is what we call the inductive hypothesis. And again, I'm just going to put this in brackets, so that way every time I talk about these things, you know what we're talking about. Okay. What we've seen is that this result holds for small values of n. Okay, so we're going to say this formula, or this result, holds true for small values of n. Because we have to state whether or not that the basis step actually does hold. Okay? If we don't write that out, then somebody that's looking at that doesn't necessarily know that the basis is valid. Okay? By the way, what happens if the basis is invalid?
Then we're going to go
You're done, right? We've actually found a counter example. Okay? And you're really lucky, because then you don't have to do all this crap. All right. So, now what we do is, if you look back up at step 2, step 2 says that we assume the result holds for all n equals k, where k is an integer. So that's what we're going to do. We're going to say, let's assume the result holds for all n equals k, where k is an integer. Okay? And I just defined a new variable, so that's why I just put k as an integer there. Okay? So we assume the result holds true for all n equals k. So now what we can say is that instead of this formula, we just replace the n's with k's. Okay, so thus 3 plus 6 plus 9 plus 12 plus da-da-da-da-da plus all the way up to 3k. And remember, we're assuming this holds true for all the k's. Okay, we don't know if it holds true for the n's, but we're assuming it holds true for k's. Okay, so that's why we just change our variable here. 3k, k plus 1, divide 2. Okay. So, if you guys can do that much on the examination, I'm inclined to give you guys 4 or 5 points out of 15. Okay, so, and I'm going to have 2 problems that involve induction. They'll each be worth 15 points. Okay? Alright, so that's step 1 and 2. Okay, now we have to do step 3, where we have to show that the result holds for every case thereafter. In other words, let's let n equal k plus 1. Okay, so we're going to prove for n equals k plus 1. Okay. So let's do that. Let's let n equal k plus 1. We're going to substitute. Okay, so we're just going to say, let's let n equal k plus 1. By substitution, the formula that we have up top, okay, or this guy right here, so 3 plus 6 plus 9 plus 12 plus da-da-da-da-da plus 3n, which is equal to 3nn plus 1 divided by 2. And we're going to substitute k plus 1. Okay, now I'm going to show you guys what it means to substitute k plus 1. Okay, on the left-hand side, we're going to go up to the k plus 1th term. So the k plus 1 term is the term after 3n in this case. Okay, so this is going to become 3 plus 6 plus 9 plus 12 plus da-da-da-da-da plus 3k plus 3 quantity k plus 1. Okay? So basically, guys, all we're doing is we're just going up one more term than what the series gives us. Okay? Does that make sense to everybody, guys? Like, this term right here is the kth term. This is the k plus 1. So here's what I always tell people. I always tell people, just rewrite what you already have, and then just add on one more term where you put k plus 1 in for n. Okay, it's the easiest thing to do for that. Okay? On the right-hand side, we just directly substitute k plus 1 back in for n. So this becomes 3 quantity k plus 1, quantity k plus 1 plus 1. You could immediately write that as k plus 2 if you wanted to, divided by 2. All right. So let me make sure that's all okay with everybody. But did I lose anybody so far, guys? Any questions? I know it's a different type of animal, and we might have to see it a few times before we truly assimilate it. But I just want to make sure everyone's good for this. So obviously on the right-hand side, we can just write that as k plus 3k plus 1 times k plus 2. So let's just go ahead and do that. We'll make that nice and easy. K plus 1, k plus 2, div 2. That's just computation. What about the left-hand side? Is there anything that we might be able to possibly do to simplify the left-hand side? And if so, what?
3k plus 3, right?
Well, I don't want to combine like terms. Okay, that's okay. That's not a bad try. Donnie?
Just add up all the stuff right now.
We could do that, okay, but we don't know the stuff in the middle, right? So unfortunately, we don't know if that's going to be like 5 terms, 55 terms, 555, and it's not a bad guess. I think that's what both you guys were thinking, combined like terms, because that's what we've done all our lives.
What about subtract them? Those 3k and 3k?
One more time?
Expand with the 3.
No, that's actually what the gentlemen were saying too. They combine like terms. John?
Factor out of 3?
Unfortunately, not a bad guess. Okay.
You subtract 3 times k plus 1
Um,
on both sides?
No, unfortunately not. Okay.
Okay, so we're all...
Okay, that's all right. It's not a bad thing. I want you guys to notice that this stuff right here might be equal to something already that we know.
Oh yeah, that's 3k.
Guys, did we say over here that 3 plus 6 plus 9 plus 12 plus 3k, whatever, and however many terms that are in here, okay? And Donnie, I think you made a good point right here that we don't know if this is 5 terms, 55 terms, 555 terms, but whatever it is, it's got to be equal to this, right?
Okay.
So what I'm going to do is I'm just going to not substitute, but it's called induction, to where I think that this is correct. I can't disprove it, so I'm going to use induction and basically substitute it for what we have over there in blue, okay? So does everybody see that what I have boxed in blue, those are identical to one another by mathematical induction, okay? So I can write this as 3k, k plus 1 divided by 2. Okay, that's what all of this stuff is, okay? It's not substitution, okay? There's a difference in math between substitution and induction. Induction means that we don't know for sure that it's true. We assume that it's true, okay? So does that make sense, guys? Substitution we know is true, okay? But unfortunately with induction, in other words, this inductive hypothesis, we think it's true. We have no reason to think anything to the contrary, okay? I'm going to write this next. I'm just going to have 3k plus 1, okay? So this guy just comes down here, or girl, I don't want to be gender biased, okay? So guys, if I wanted to justify that step, I would either say induction, okay? Actually, I would say induction, and then the other step that we have over there, that's just a basic computation, the k plus 1 plus 1. Okay. So this is the process for the induction so far. Okay, I don't think I've lost anybody with this. Every time, whenever you guys do an induction problem, you're going to substitute this, even though it's not substitution. You think of it like substitution. And you're going to substitute the right-hand side back in for this potentially very lengthy number of terms. All right. Now, we're still not done, but at least we have a punching chance to get done with this because the rest of it's algebra. I need to make the left-hand side look like the right-hand side of this. Okay? Does anybody think they might know a way to start?
Bring it the right side to the left and make it equal to 0?
Well, no, we don't want to set it equal to 0. Let's just work on one side, just like a trigonometric proof. Okay. Maybe we want to hold one side constant.
Multiply both sides by 2?
That's one way to do it, or we can just get a common denominator for the right and the left-hand side and then try to merge it together. Either way you want to do it, okay? technically, in mathematical proof, you want to hold one side constant and then operate on the other side, okay? Just like, and I don't know like how many of you guys remember doing the identities in trig, but when you prove an identity, you should hold one side constant and not mess with the other side. So I'm going to do it the classical way. If you guys multiply by 2, that's fine with me, okay? So let's do this. Let's get an LCD of 2. So the first term stays 3k, k plus 1 over 2. What about that second term? Instead of 3 quantity k plus 1, what's that going to become, guys? 6 quantity k plus 1, right? Basically, if you give it a denominator of 2, you multiply the numerator by 2, right? So this is going to become 6 quantity k plus 1 divided by 2. And then we can go ahead and say that that's going to be equal to whatever we had on the right side to start with. Okay. So does that hurt anybody's feelings, or is that okay so far? Okay. So let's make this into one mega fraction now. I mean, that's the whole purpose of getting a common denominator. Okay. In fact, if you guys wanted to skip right from the inductive step to this next step that we have, you certainly can. Okay. So just by addition. By the way, we're 2 steps away from getting done this problem. Okay. So by addition, this is going to become 3k, k plus 1, plus 6 quantity k plus 1 divided by 2, and that's going to be equal to the right-hand side. Okay, so let me get out of your guys' way. I'm going to make up a little bit more room for myself. Like I said, 2 more steps algebraically, maybe even 1. Okay. So we still want to make this left-hand side look like the right-hand side. And there's 2 ways that we could potentially do that. Okay? Does anybody think they might have an idea of what to operate on the left-hand side? And there's, like I said, there's 2 ways to do it. I'm going to try to show you guys an efficient way, but I bet you guys know a couple ways to do it. So what's one thing you guys might do? Go ahead, Paul.
Can you factor out 3?
We could not only factor out a 3, but what else, guys?
K.
3 quantity k plus 1. Very nice, gentlemen. Okay? Guys, is it obvious to everybody that 3 and 6 share a factor of 3? Is it obvious to everybody that k plus 1 and k plus 1 share a factor of k plus 1, right? So we could factor that out as a GCF. What's another way that you guys might be able to do that?
You could multiply it out.
Foil it out and then do like the factorization that way. Okay? I don't care which way you guys do it, but I think I like John and Paul's way of doing it a little bit better, to where you look for a common factor and pull it out. It'll save you guys 2 or 3 steps, okay? And we want to be efficient. Okay, that's just a nice word for lazy. Okay? So, if I were to factor out the greatest common factor of 3 quantity k plus 1, guys, if you factor out 3 k plus 1 from this first term, guys, what are we left with in the first term?
K plus 2.
Just k, right? So I'm just going to be left with a k. If I was to factor out 3k plus 1 from the second term, what are we left with there, guys?
2.
2. Okay. If you don't trust me, just go ahead and FOIL it back out. Okay. And then on the right-hand side, we're looking for 3k plus 1, k plus 2 divided by 2. All right. So guys, it's a little bit simple, okay? But you're going to look for sometimes binomial factors. You're going to look for like GCFs a lot of times when you have these fraction sort of problems. Okay? Is everyone okay with the factoring here, guys? Okay. If you can't see the factorization, make sure you see me after class so I can help you see that a little better. Or maybe what Mr. Weber was saying is just FOIL it out and brute force it from there. Okay. You might be able to do your trinomials better than you can in GCFs. Okay. Guys, we've shown it to be true, right? Isn't this sort of like division into cases? We had a basis step and then we have an inductive step. We've proven them both. Okay, so therefore, by the basis and inductive steps, the formula is true. You don't have to write this down, I'm just writing something that remember seeing like a geometric series, right? And for those of you guys that are suffering through Calc 2, and it has a form, right? It's all, what is it, 1 over, A over 1 minus R, right? You can prove the sum of a geometric series true by using mathematical induction, okay? Now the problem is because it's infinite, it's difficult to do, okay? But you guys could be able to prove that, okay? So for those of you guys that are suffering through any Calc 2 stuff, eventually you'll see your series, and that might be helpful for you. But anyway, I just wanted to tell you guys in real life that this does have applications. It's not just something that math people come up with to torture you guys, okay? All right, what's that? Well, Calc 2 was developed to torture everybody. Yeah, sorry about that. Okay, questions I can answer, guys? Okay, now obviously, we need to see more of these, okay? So, by the way, on a scale of 1 to 10, this guy was about a 2. I never give anything a 1 from induction because, well, it's just all different. All right, so let's beat up another problem, okay? So this time, I'm asking you guys to prove that the sum of the first n perfect squares is equal to this mess right here, okay? Maybe some of you guys in Calc 1, how many guys did like the Riemann sums in Calc 1 where you had to like do you actually had to find the forms of the rectangles and try to add them up that way? You might have used this formula at some point to write it, okay? We're actually going to prove that formula, okay? I kind of cheat my Calc 1 class out of doing that because it's just kind of unnecessary. But regardless, okay. So here's our proof, okay? We need a basis step. Okay. Let's just use n equals 3, just because. And then from now on, we'll just go ahead and use the first element in the domain from now on, or after this case, okay? So our lowest element in the domain could be 1. Let's just do 1, 2, and 3. So let's let n equal 3. This means that 1 square plus 2 square plus 3 square should be equal to 3, 3 plus 1, 2 times 3 plus 1, all divided by 6. Well, let's hope that's true.
How do you decide what n equals?
That's a good question. Okay, John, I can make n equal anything I want as long as it's the number in the domain. Okay? I could have used 1 if I wanted
As
to.
long as n is greater or equal to 1.
Correct, sir. Okay? I'm only using 2 and 3 initially just to show you guys how to get these to work. After that, we'll just use 1 from now on. Okay? But I just wanted to make sure, like, if for some reason another one of your teachers says, use something other than the most simplistic case, then we've done that. Okay? Does that answer your question, sir?
Yeah.
Okay, good. All right. If we compute this out, and of course it's addition, so you might not want to trust me. 1 plus 4 is 5. 5 plus 9 is 14. On the right-hand side, 3 times 4 is going to be 12. 12 times 7 is going to be 84. 84, 6 is 14, I believe. And so I can verify. Oh, it should be multiplication. I should be okay with that. Adam, is that good? Yeah. Okay, thank you, sir. And guys, last time I checked, 14 does equal 14. Okay, so right there, guys, that's easy to do. We can all do that no matter who we are in this class. I know you guys can. All right. Step 2 is the inductive step. We have to assume that this holds true for all n equals k. Okay, so step 2, and again, for the first couple times, I'm just going to put this in brackets. This is the inductive hypothesis. We assume, it looks like the result holds for small values of n. Okay, so we're going to say the result holds for small values of n. In other words, we can't find a counterexample. Okay? Not that we tried very hard, okay, but we could if we really wanted to try hard, but we would assume that it works if we find something small and it works. Okay? Now we assume the result holds true for all n equals k. Okay, so let's go over here. We'll erase some board. So let's assume the result holds true for all n equals k where k is an integer. Okay. Thus, the sum of the first kth perfect square, so 1 square plus 2 square plus 3 square plus da 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 plus k square now is going to be equal to k plus 1, 2k plus 1, quantity, divided by 6. Okay. Now, that's an assumption. Okay? We don't know that for sure, but we can't find a counterexample. Okay? So, let me give you guys a minute, copy that all down. Okay, so everybody's good with the preliminary stuff. No questions about basis, no questions about inductive stuff. Okay, now comes the fun part. And when I say fun, I mean, this is the part you want to pull your hair out of. We have to show it true for n equals k plus 1. Okay, so this is where we make our money with our algebra. Okay, so 3, we want to prove for n equals k plus 1. Let's let n equal k plus 1 by substitution let's go ahead and make sure we can write this. Okay? So by substitution, does anybody think they might know? Well, I'm going to write out what we initially had. So let me do that. So we have 1 square plus 2 square plus 3 square plus da 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 plus n square is equal to n plus 1, 2n plus 1 over 6. Okay, that's just the original that we were given. Does anybody think they might know what's going to look, or what it's going to look like after we perform the substitution where n is equal to k plus 1? Mr. Hart, go ahead, sir.
N plus 1 square plus n plus 2 square, right, on the left-hand side?
Well, say it one more time for the entire thing.
Okay, on the left-hand side,
Okay.
it will become like 1 square plus 2 square
Yes, sir.
plus 3 square
Yes, sir.
plus da 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 n plus 1 square.
Not quite. You're really close. Okay? Somebody help him out. You're really, really
Plus n
close.
squared, or plus k squared,
Uh-huh.
Oh, k square, yeah.
plus quantity k plus 1
Nice.
squared.
That's the only thing I was missing, that k squared.
First.
Okay, very nice job, Mr. Weber. Okay? Guys, does everybody see how they did that with that? Okay? All they did was they just went up to k, so they just basically plugged in k for n, and then they just added on one more term, the k plus 1 term. Okay? The right-hand side, don't we just go ahead and substitute k plus 1 in wherever we see an n? Now be careful, okay? I'm going to write this up incorrectly, and then somebody yell at me as to why I write this up incorrectly, please. So k plus 1, quantity, k plus 1 quantity, 2k plus 1 quantity, divided by 6. Okay, so let me let you guys copy it down, and then I'll let somebody yell at me. But what did I do incorrectly there, unfortunately? Yeah, guys, and a lot of students unfortunately do this. Right here you have 2 times n, and they substitute k plus 1. Please, please, please don't forget that it's the quantity of k plus 1, okay? And then unfortunately what will happen if you forget to do that, your proof's not going to look right, or it's not going to go right, and then you're going to get really upset because you went through the whole problem. Alright, and you'll start cursing my name even more than you already do. Okay, I don't need that. My soon-to-be ex-wife is already cursing my name and taking my money anyway. Okay? Oh, it's okay, don't worry, she's rich. Right. Questions I can answer, guys. Everyone's good with being able to substitute up to the k plus 1. Everyone's okay being able to substitute k plus 1 on the right side. Okay? So, after this, most students do really well if they get this far. Alright. On the right-hand side, can't we just simplify the numerator a little bit? We're not going to FOIL anything out. We're just going to write it as k plus 1, k plus 2, 2k plus 3 over 6. So let's go ahead and do that. That's computation. So k plus 1, k plus 2, 2k plus 3 divided by 6. What about that left-hand side, guys? What's the trick that we need to utilize at this point to maybe have a punching chance at this?
Induction.
Right, we need the induction step. What are we substituting by induction, guys?
The whole sequence.
Except for?
Except for that last term that you
Correct.
had k plus 1 squared.
Yes, sir. So Greg, we're going to substitute 1 for 1 squared plus 2 squared plus 3 squared up to k squared. And what are we going to substitute for that, sir? Yep, this ugly ass formula right here, right guys? So we're just going to plug all of that in. So that's going to be k plus 1, 2k plus 1, all divided by 6, okay? And that's not substitution, that's induction, okay? If you do write induction on the examination, or if you write substitution, it'll cost you a point, because technically it's one of the most important steps. And I want to make sure you guys understand the difference between induction, which is an assumption, and substitution, which is a given, okay? So, this is just by induction. I'm going to copy down this k plus 1 square term as well. Okay, and that just comes down. Okay. So this is just by induction / computation. All right. So that's fun. All right. The rest of the problem is very similar to the previous. Okay. So somebody remind me, because I forget everything already. Okay. What do we have to try to do to make left-hand side look like right-hand side? Or what did we do in the previous problem? Common denominator. Nice, John. Guys, isn't the common denominator 6 for this problem? Okay, we can obviously see there's a denominator of 6, so let's get that. And what I'm going to do is I'm just going to immediately write this as one mega fraction, if you would. Okay, so if somebody will check me just to make sure that this is good, k plus 1, 2k plus 1, plus 6 quantity, k plus 1 square, divided by 6. Okay? Does that look like a good mega fraction? Or at least for this problem. Maybe it doesn't look good. Okay? I mean, I think it's sexy, but, you know, what do I know? All right. The right-hand side looks exactly like what we already had from before. Okay? So right-hand side, k plus 1, k plus 2, 2k plus 3 over 6. So we're not going to mess with that. All right. Now, just like the previous problem, okay, there's going to be 2 ways that we can approach this. We can look for a GCF, or we could FOIL it out. What's the detriment to FOILing that out and then trying to factor it after that?
It's too big.
It's going to be a cubic, right? And how many of us want to use the rational zeros theorem to try to factor it out? How many of us even remember the rational zeros theorem? Go ahead and answer that. I'll pretend you guys did. All right. So, unfortunately, guys, if you do FOIL this out, you're going to get a 2k cubed. And you don't want to work with a cubic and try to factor it. Okay, it's probably not going to factor like by grouping. So, if I was to ask you guys for a common factor, what's the GCF in these 2 terms, guys?
K plus 1.
K plus 1, right? There's a singular k plus 1 that we can factor out. Let's factor it out. Okay, so we're going to go over here. Get a little bit more room to work with. So we're just going to pull a GCF out of k plus 1. Okay. So I'm going to pull out this k plus 1. We're still going to be dividing by 6. It's still going to be equal to that right-hand side. So there's nothing really what we're doing to the right-hand side until the very end of the problem. Can somebody tell me, if I was to factor out the k plus 1 from both of the terms that we have, does somebody think they might know what would be the remaining polynomial without FOILing it out as when we factor that
K,
GCF out?
2k plus 1.
Okay, so k, 2k plus 1, that's the first term. So we just lose the k plus 1 that's there. Okay.
Plus 6, k plus 1.
So we only lost one of those 2 k plus 1s, right guys? Right. Okay. What if you don't trust that? Don't you just go ahead and FOIL the k plus 1 back through? Okay. And if you don't trust that, then, well, I don't know what you learned in factoring. Okay. All right. Look good, guys? Any questions? Okay. Yeah, it might not look good, but does it look correct? Let's just say that. Okay. It might not look good, but it's correct. All right. Still doesn't look like the right-hand side. There's no common factors here. So does anybody have a suggestion at this point, guys?
Give up.
Give up. That's a good suggestion, okay? I'd like that. Unfortunately, there's 25 young minds I have to make sure that get onto the next class from this stuff. So let's just assume that giving up is not an option. Giving up and drinking? Oh, that's an even better option. All right. Let's say any sort of thing that'll help us lead to the correct solution of
We
this.
can use k plus 6 as one more fraction too, right? K, that's not going to solve anything, but it can.
Maybe something better than that. Well, it's not algebraically incorrect. It's not going to get us to the answer. Yeah, let's just FOIL out that stuff, okay? So let's just FOIL out, collect like terms in there. Usually we don't like to FOIL, but in this case we don't have an option. There's no other common factors, okay? So, just by multiplying and addition, so just some basic polynomial operations, k plus 1. If I was to FOIL this animal out, wouldn't I give it 2k squared for the first term? I have a 1k and a 6k. So it just becomes 7k's. And then I just have a 6 plus 1, or 6 times 1, which is a 6. All divided by 6. All right, so like I say, guys, we usually don't like to do that, but in this case, it's unfortunately the only way that we can go with this. Okay, is everyone okay, by the way, how I FOILed that out and collected like terms? Okay, just did just our distribution and collection. All right, is it possible that this trinomial might factor into something nice? And if it does factor into something nice, yeah, it just might factor into what? Maybe k plus 2, quantity 2k plus 3?
That's what I'm saying.
That's what I'm saying. Now, what if we don't know that? Well, we just guess, right? I mean, I wouldn't give you guys the proof. And then once we guess it, couldn't we just FOIL it back out to see if it works? So even if you're not a master at factoring your trinomials, you can just assume it's going to factor into this and just FOIL it out and see if it works, okay? Now that doesn't work in any other math class because most of the time your teacher says just factor it and do it, and they don't give you the answer beforehand, okay? But that's going to be equal to what we need. Now we can give up because we're done. Yeah, at least for this problem. Sorry. Yeah, I know. I know, I'm sorry. It's tragic.
Are you going to crush my dreams every single time, Chris?
I know. What's that?
Are you going to crush my dreams every single time?
You know what, John? I'm sorry. That's just what math teachers do. We just like to build you up just a little bit so you think you're doing something right, and we just like to make you feel small again. Okay?
Maybe I'm a mess.
Did you say there was going to be 5 of these on the test?
You know what? For everyone else, it's going to be 2, but for you, it's only going to be 5, just because I'm a nice guy. No, just 2. Okay? Yeah, these are the hardest ones, but they will be worth 15 points in each.
They are not hard, it's long.
They are, you're right. You know what, and I might have said this before, I equate it to mowing my lawn. They're not difficult, but I gotta do it sort of thing, and it might just take forever. Okay. All right, everybody good with this, guys? We'll finish this off. We'll say, therefore, by basis and inductive steps, John's dreams are crushed. Oh no, the result holds.
It's okay, they're basically made of glass.
Do you need a hug, brother? Seriously. I'm starting to feel bad for you.
Can we also say the formula is true?
Sure, absolutely. If you want to say, because that's really what it is. It's a formula for the sum of the first kth or nth terms. Okay? Yeah, whichever way you want to do it. Okay, John?
Can you explain the inductive hypothesis?
Absolutely. John, didn't we say before that we assume that 1 plus 2 plus 3 plus k squared is equal to this? That's what we assume to be true. Okay?
Where did the k come from?
Well, remember, we assumed it true for all n equals k's. So we have to use a different variable because we're assuming. Okay? So we just basically plugged in k. That's all we did. And then down here, when we let n equal k plus 1, that's where we utilize the inductive step. Okay? So does that make a little more sense?
No, because can you
Right, the beginning part?
Yeah.
Okay, so because this is valid, so basically if the basis is valid, then you just say, okay, well, I know it's true for small n, then I just want to assume it true for a different variable. Let's call that k. Okay? So we just make a different variable because we have to assume it to be valid.
Okay, so you're just swapping.
Yep, we're just swapping variables because we're assuming it true for a different one. Okay, does that help, John?
Yeah.
Okay. Other questions, guys? Okay. So, this time we'll deal with some exponential expressions. Okay, so the other ones, we started with linear, now we went to quadratic ones. Let's go ahead and do exponentials. So I want to prove that the first n base 4 sums is equal to 4n plus 1 minus 3 over 3. Okay, so let's go ahead and prove, or disprove. It'd be really nice if we could disprove it, right? Because then we'd be done.
Well, one of the 2 questions on the exam disproved, so we can finish after like the second step.
You know what? You could try to disprove it, but they won't work. Sorry. And I'll make sure that I work through the exam before I give it to you guys to make sure that they all work. So, by the way, if you guys get a problem for homework that doesn't work, you're wrong. Okay? I always make sure that they all work, okay, beforehand. So sorry about that. And same thing on the examination. So if you just say I disprove this, go back and do it again unless you want to start with like a B instead of an A. All right. So we want to do our basis step. Okay, so we're approved. Let's just go ahead and let's let n equal 1 this time. Okay, because the other times we've been letting n equal 2 and 3. So let's let n equal 1. Okay. What would that look like, guys, if I let n equal 1? 1 equals 4 to the 1 plus 1, okay, minus 1 divided by 3, right, guys? So, well, this one doesn't work out.
It's 4, it's 4. The first one's 4,
Oh.
not 1.
Wait, where?
The one on the
Four
right,
to
the
the power
left,
of
the
one
left
is
is
four.
bigger than 4.
Oh, no, it doesn't.
No, wait,
No,
the
it's
first
one.
one is 1.
Yeah, the first one's 1. So, you know what?
So it doesn't.
But
No,
the
it
problem
does.
is
There we go. Sorry. After I just got done saying none of them work. Of course. Alright. I just put the wrong domain value in there. I'm sorry, that's a copy error. Okay. Now you can't do that on the test. Okay, you can't just scratch out the number and substitute whatever you want. So,
So now we have a new 1 plus.
Still doesn't work.
no, it does. Okay. So, this is going to be 0. So this is the 0th term. Okay, so really what happens is we start like a new index. Okay, so this would be, the 1 would be the 0th, 4 would be the first, 4 squared would be the second. Okay, so yeah, so we're going to let n equal 0. Okay. Sorry about that. So this guy right here is the 0th term. Okay, so whatever the initial value is in the index or in the domain, that's where you guys start at. So if I just said for n equals -5, 1 would be -5, 4 would be -4, 4 squared would be -3, just like an array. Okay, same sort of thing. Right? This time it does work because 1 is going to be equal to 3 divided by 3. Okay.
So in a case like this, if we set n equal to 1, it would have to be 1 plus 4.
Right, that's correct, because it would be the 0th and the first term. Okay, and that will give you 5, and then over here that will give you 15/3, which would still be valid. Okay, yeah, that's correct. Okay, does that make sense to everybody, guys? If the domain starts at 0, this is the 0th term. Okay, so obviously the basis step holds. Okay, so our second step, the inductive hypothesis. Thus, the basis holds for small values of n. Let's assume the result holds. So we assume the result holds for all n equals k, where k is an integer. Okay. Thus, instead of using n's, we're going to use k's in now our formula. So thus, 1 plus 4 plus 4 squared plus 4 to the third plus 4 to the fourth plus plus 4 to the k now is going to be hopefully equal to 4 to the k plus 1 minus 1 divided by. Okay, so let me give you guys a chance to copy that down. While you guys are doing that, I'll erase it over here. But any questions about either our basis or our inductive steps? Okay, hopefully they're not too difficult for you guys. I'm assuming that the third step is going to be the tough part for everybody. Okay, so no questions, guys? Okay. So, now let's do our substitution step. Let's let n equal k plus 1. So, third step. Let's let n equal k plus 1. Okay, by substitution. We are going to say that the original formula, 1 plus 4 plus 4 squared plus 4 cubed plus 4 to the 4th plus plus 4 to the n, which is equal to 4 to the n plus 1 minus 1 over 3. Okay. Now is going to become the exact same thing, except now we substitute k plus 1 back in. Okay. So, does somebody think they might know what this is going to look like after we substitute k plus 1 back in for this?
Mhm.
Okay. So, are we
Same
got this
thing,
time?
yeah. 1 plus 4
Mhm.
plus 4 square
Uh-huh.
plus 4 cube plus 4 to the power 4
Uh-huh.
plus all the way to the 4 to the power k
Uh-huh.
plus 4 to the power k plus 1.
Perfect. Thank you, sir. Okay. So, guys, do you see what he did there? He just took and copied the exact same thing down. He just plugged in a k, and then he just went one more term. That's the k plus 1th term. On the right-hand side, 4k plus 1 minus 1 over 3. So 4k plus 1 minus 1 divided 3. Okay. So, let me make sure that's okay with everybody. Okay, I'll give you guys a second to copy that down and then a chance to ask me some questions. Okay. Just a lot of copying, right, guys? Okay, same stuff over and over and over again. That's why sometimes students think these are tough, but it's really just copying. Okay. So, as we've seen in the other two examples, okay, what's the next step that you guys might think we'd have to do with
Inductive
this?
step.
We can do induction, and then the other thing we do is...
Lowest common denominator.
but after that, right, you're right, Greg. Hold on to that for 1 second.
Computation.
Computation, right on the right-hand side, there's a really basic computation, okay? And Greg, you're absolutely correct, sir, okay? So, all of this mess, by the inductive hypothesis, is going to become 4 to the k plus 1 minus 1 div 3. We still have that 4 to the k plus 1 from before. And then that's going to be equal to 4 to the k plus 2 minus 1. Minus 1. Okay, so let me make sure everybody's good with that. Okay. But we've seen it already 2 times today, or to where we just all have to go ahead, do the inductive step. All right, and once we do the inductive step, then we just go ahead and have to do a substitution. Okay, so this is, oh, go ahead.
So for like the second step, what would you call that, like for,
Oh, from here to here, or?
like that one step, like, cause we have to write down like our steps of what.
Oh, right, yeah, this is induction.
Well, yeah, like, I mean like the one on top of that.
Oh, that's just by substitution. Okay, so we just did substitution right there. We
Oh,
are
so
just,
the middle one substitution?
correct, yeah, I just didn't have enough line or enough space to write it all the way out, so I just went down to the next line. Okay, is that all good? Sure. So the induction slash computation. Okay. Greg, you foresaw a minute into the future, and what did you foresee? The least common denominator, okay? Let's just make this into one mega fraction. And we're going to be really careful when we make this into a mega fraction. All right, I'm going to write this incorrectly, okay? Don't copy it all the way down. And then you guys are going to tell me what I did incorrectly, okay? So this is going to be 4 to the k plus 1 minus 1 plus 12 to the k plus 1 divided by 3, okay? And that's going to be equal to the right-hand side.
We'll do 3 dot.
Okay. Right. Guys, unfortunately, this is not correct. Okay? Now, everybody sees that to go from 3 to the common denominator, you just multiply this by 3, right? Okay? But this is not correct. So don't do that. Okay? Or what were you going to suggest it would look equal to?
3 dot.
3 times 4 to the k plus 1. Okay? These two are not the same. This would have to be a 3 to the k plus 1. for me to be able to merge those two into a singular term, or into a simplified form of that, okay? So does that make sense, guys? You can't multiply these because they have different exponents. 3 has an exponent of 1, 4 has an exponent of k plus 1. It's just like radicals. You can't multiply unlike radicals. You can't multiply unlike exponents. Okay, so everybody good with that, guys? Any questions thus far? Okay, so here comes the tricky, oh, by the way, this is just LCD. This is the tricky part for some students, okay? They're not quite sure what to do at this point, even though we're really close to the solution. So let me go over here. Give us a little more space to work with. Does anybody think they might know what to do in the numerator at this point to kind of make it look like 4 to the k plus 2?
Take 4k plus 1 common and then subtract 1 from 3. That will be like 2.
Unfortunately not, no. We can't combine like the 1 with anything. Okay, the 1's just completely different. Okay.
John, can you add the 4 to the k plus 1 to the other one and change the 3 to a 4?
So, John, what you're saying is that this has base k plus 1. This has base k plus 1. So basically they're like terms. Like for instance, if you had 1x plus 3x, that would be 4x, right guys? If you have 1k to the plus 4 plus 1, and you have 3 4 to the k plus 1s, guys, how many 4 to the k plus 1s do we have? 4, right guys? Doesn't that make sense? There's 1 of these and 3 of these, okay? It's just like, and just throw an x in front of it if you don't believe me. 1x and 3x is 4x. So could I not rewrite the numerator as 4 times 4 to the k plus 1 minus 1 divided by 3? Just by combining like terms. Now, when we say like terms, okay, these are big boy like terms, okay, not like 1x and 3x, okay? That's easy stuff from Algebra 1. So, does everybody see how that works, guys? It's a little bit sneaky, okay? Because normally we don't think of exponential expressions as like terms, but in this case, we just have to force them to look like terms. Okay? All right, we're basically done because, guys, can we see that over here you have 4 times 4 to the k plus 1, right? Well, what's the rule if you multiply common bases? You just add the exponents, okay? And Lauren, by multivariable calculus methods, 1 plus 1. Very nice, awesome. Scholar of the year right there. Awesome. But Lauren, you just proved that it works at this point, right? Because doesn't the left-hand side now look like the right-hand side?
Yes, it does.
Absolutely. And we've done it. Does everybody see how that works, guys? It's like if you have an x squared and an x cubed, that becomes x5, because you just add 2 and 3. You have 4 to the first and 4 to the k plus 1. So 1 plus 1 gives you the 2. Okay? So, John?
Do you want to do the like term stuff again?
Oh, back here, right, sir? Okay. John, think of this as 1 times 4 to the k plus 1. Think of this as 3 times k plus 1. In fact, if you wanted to, you could assign x to be 4 to the k plus 1, and you could see that if you have 1x plus 3x, that would be 4x's. Got it?
Yep.
Does that help to see it a little bit better?
Yep.
It's almost like that transitivity property. Or maybe when you were pre-calc, you did those horrible
Please
view
don't
substitutions.
give something like this in the exam.
Oh no, I'll only give you like 5 of these. Don't worry about it. Everybody else will only get like 1. No. Yeah, these are tough because they're a different way of thinking.
What are you calling the last step?
Oh, the last step, I'm not calling anything yet. But this is just, technically it's the product rule of powers, but we could just say exponent rules if you wanted to. Okay? Because that's literally what we're doing, is we're just using some exponent rules. Okay. Alright guys, so we're done with this, right? We have a basis step, we have an inductive step, done. Okay, so, therefore, by basis and inductive steps, the result holds. Okay, or formula holds, or I'm done with this, I've been tortured enough, whatever you want to put up there. Okay, Blue Jays suck.
I have a question. We don't have any of these on our homework that do.
No, these aren't on assignment 6, but these are on assignment 7, which is due the day after the examination. Okay, so, and what I would
These
do...
are on the examination.
Yes, sir. Yeah. Sorry, they are proofs. I try to keep all the proofs together just because they're just basically similar problems. So I wouldn't want to divvy them up and make you guys do the same thing twice. Okay. All right. Other questions, guys, I can answer about anything so far? Okay. We've done 3 of these types of problems that just have they just have it listed out explicitly. Okay. Let's go ahead and try to look at a series type of problem. Okay. So I want to prove that the sum of the first n perfect cubes is equal to that monstrosity right there. Okay. So let's go ahead and see if we can do that. Okay. So first thing we need to do is we need to have a basis step. Okay. So and the basis step we could just use 1 for our lower part of the domain. Okay. So let's just go ahead and do that. All right, so let's go ahead and start by saying, let's let n equal 1. Okay, so we'll just start at the lowest part of the domain. If n is equal to 1, wouldn't this series become I equals 1 to 1 of I cubed? Okay, so that would be I equals 1 to 1, since that's what n is, of I cubed. On the right-hand side, this would be 1 square, 1 plus 1 square, divided by 4. What do I have to do to be able to evaluate the left-hand side, guys?
You have to add them, see?
Yeah, we just have to add up the first of those terms, right? Well, how many terms are we really adding up there, guys?
1.
Just the first term, right? What if this was 2? Didn't we go through that on Monday, guys, where you just have to plug in 1 and then plug in 2 to that and add them up? If it was 3, that would be 1 cubed plus 2 cubed plus 3 cubed. Okay, so it's just the same thing that we did on Monday with our series. So this just becomes 1 cubed is going to be equal to 1 square times 2 square over 4. Okay, and guys, doesn't it look like for this one, 1 does equal 1? Okay, I think that's fairly obvious. So 1 equals 1, and we're good with that. Okay.
No, but it's becoming half. 1 square. Oh, yes. Yes.
Promise?
No.
Okay. All right. So other questions, guys?
Where did 1 cube come from?
Remember,
it's right in front of me.
Andre, this is the series, right?
Oh, you plugged it in.
Right.
Oh,
So we
okay.
just plugged n equals 1 back into the original series right here. All good, sir? That's okay. You've been beat up on math for an hour, so it's okay to not see anything. All right, guys, we assume the result holds for all n equals k. Okay, so we say the basis holds for all small values, or holds for small values of n. Then we assume the result holds. So assume the result holds for all n equals k, where k is an integer. Okay? Therefore, we just replace all the n's with k's. We don't touch the i's. Okay? Generally, I'll get a couple students that when they rewrite this with a series, they'll mess with the I. Okay? Never mess with the i's in there. Those are basically going to be the function component, or the sequence. Okay? So this is going to be thus series I equals 1 to k, or I'm sorry, yeah, to k, excuse me, of I cubed is going to be equal to k squared, k plus 1 quantity squared, divided by 4. So those are easy, right, guys? Those are free points for this problem. We basically just do a computation, we do a substitution, okay? Not difficult. Okay. Now, this is where some students get tripped up with this because they don't like the k plus 1 with the series, okay? It's not that big of a deal, okay? So, we're going to let n equal k plus 1. We're going to substitute. So, by substitution, Guys, doesn't this become now I equals 1 to k plus 1, right? So the series, so the original series that we had, I equals 1 to n of I cubed, which was equal to n squared, n plus 1 squared, divided by 4, is now going to become series I equals 1 to k plus 1 of I cubed. Again, notice that I did not mess with the index I. The only thing that I changed was I just changed the upper bound for this, okay? So I'm just substituting for n's, okay? So don't try to get fancy with it, just substitute for n. That's going to be equal, hopefully, to k plus 1 squared, k plus 1 squared, divided by 4. Okay, so let me give you guys a moment, make sure that's all okay. But everybody's okay with this so far, guys? Didn't do anything too fancy or too difficult with this. All I'm doing is I'm just substituting back in, okay, for the original formula, and just substituting back in k plus 1 for this. Okay. Now, for all the other problems, it was really easy to do the inductive step. But this time, we can't substitute or do induction yet because we don't have I equals 1 to k of I cubed, okay, on the left side. So does anybody think they might have an idea as to perhaps how we can try to rewrite the left side so that we get something that looks like this? Yeah, sneaky, right, guys? Okay. Guys, don't we have I equals 1 to k plus 1 on the left side, right? Couldn't we just break off a k plus 1? And wouldn't that give us all the terms up to k, and then that k plus 1? So what I'm going to do is, let's rewrite it like this, and maybe you guys will see. I equals 1 to k of I cubed plus quantity k plus 1 cubed. Right, all I did there was I just plugged in k plus 1, which is the top term, and then I'm left with everything just before that, which is the kth term, okay? Does it, I think, John, I like the way that you said it. I like that you said you just plugged in k plus 1, and then you're just left with k there, okay? Does that make sense to everybody, guys? You're just breaking off everything prior to k plus 1. So that's what this is. It's just basically a rule of summation where you just pull off the kth term, and you're just left with everything thereafter. The right-hand side, k plus 1 squared, k plus 2 squared. Divided by 4. Okay. And again, guys, that's just by going through. We're just using summation rules. Okay, we're using a summation rule. And I'm going to put this in brackets. What we're really doing is we're breaking off the k plus 1 term. Okay.
So if that was I squared or I did the fourth instead of cubed, it would be squared.
Correct, right. And if this was k plus 2, you would have a k plus 2 and then a k plus 1 in there to get down to k. Okay?
Yeah.
If it was a
you have
k
to work
plus
your
3,
way down.
right, you just want to work your way down. Okay? By the way, for those of you guys that have to take differential equations, you're going to be using this more times than you ever care to count. Okay? You just have to go through and break those off when you're trying to find a series solution. Okay? Happens all the time. Okay? So that's a summation rule, and also you're going to go through and do that as a computation. Okay. Right. Guys, isn't it obvious now that you guys can just use mathematical induction right here? Because isn't I equal 1 to k of I cubed? That's just going to be equal to k squared, k plus 1 squared over 4. Okay? So let's just do the induction and then common denominator it, and we're going to see that it works out really nicely. Okay, just like all the other ones do. Okay, so by induction, we're going to go ahead and replace sum of I cubed, okay, with k squared times k plus 1 squared divided by 4. We still have the k plus 1 cubed. Alright. And some of you guys aren't liking that, but that's okay. It'll work out nicely. That's equal to the right-hand side. Okay. All right. Everybody good with this, guys? Any questions? Just went through, basically just replaced, and I'll box this in blue so that way you guys can see it. Just replace the summation with the inductive hypothesis right there. Okay? All right, guys, every other problem we've done so far, what's the next step? Common denominator, right? In this case, the common denominator is 4. Everybody sees this. So we can rewrite this using an LCD. Then we're going to get k squared, k plus 1 squared, plus 4 k plus 1 cubes, all divided by 4. Okay, and we're going to hope that equals the right-hand side. I don't think there's anybody in here that wants to FOIL that in, because now you get a 4th degree polynomial. Okay, you don't want to deal factoring with that. We don't want to deal with even factoring 2nd degree polynomials. Okay, so we're going to try to factor a GCF out if we can. Guys, what is the GCF between those two terms? K plus 1 squared, right? Guys, we see that both of those have at least 2 k plus 1s in them. So let's factor the k plus 1 squared out. So this is our GCF. K plus 1 squared. And then, can somebody tell me what's going to be left over inside the brackets once we pull out 2 of those k plus 1s?
K square plus 4k plus 1.
Square.
4k plus 1.
Good. Okay, now it's still all over 4, but at least now we don't even have to deal with a quartic sort of polynomial. We just have to deal with some sort of quadratic. Okay? So we don't like 4th order polynomials. We like 2nd degree polynomials. Okay? Suggestion at this point, guys, we're 2 steps away from being done. Yeah, multiply the 4 through, ladies and gentlemen. So let's multiply that out. So by multiplication, k plus 1 squared, quantity, k squared plus 4k plus 4, divided by 4. And please, dear God, don't tell me that you can cross out those 4s like my Algebra 1 class tells me that they can do, and I just want to backhand them. I want to, but I won't. Okay? Instead of crossing out those 4s, what are we going to do, guys? We're going to factor. Donnie, what does that factor into, sir? Do you know? The stuff on top. K plus 1. Right, and you might not even know that, but you probably can think that it's going to factor into k plus 2 squared, right? And in fact, it actually is, right, guys? Isn't this a perfect square trinomial? And it fits the form, so it's k plus 2 squared, even if you didn't know it. And Donnie, if you didn't, couldn't you FOIL it out if you really wanted to? Or you just use your TI-89, whatever it is. Oh, okay, gotcha. Gotcha, okay. Well, good for you. I'm proud of you that you don't have to rely on a computer algebra system to do your dirty work. Yeah, that's just by factoring. And we're done, right, guys? Well, we've been done for like about an hour. Right? But now we're really done with this problem. Okay? So, is that good with everybody, guys? Okay? And if you can't see the factorization, okay, just assume it factors into it and then FOIL it out just to check it. Okay? Never hurts to do that. Okay? So we can say basis and inductive step, the result holds. Okay, so therefore, by basis and inductive steps we did, the result holds. All right. Just to let you guys know, for those of you guys that are computer science majors, okay, I remember when I was taking algorithm analysis that we had to prove something ran in a specific time, okay, that ran in logarithmic time. To be able to prove it, we had to use mathematical induction to prove that the program ran recursively for the first instance, the second instance, each instance thereafter, okay? So just an application in mathematics, we use it all the time to prove things. In computer science, you can use it to prove runtimes. So induction is a very, very powerful methodology. I remember even in differential or in integral transforms, we proved something with a factorial utilizing this. Okay, I think it was like a gamma series. Or
Who
something
came
like
up with
that.
this concept?
Oh, somebody. Gossip.
Just before I forget, do you have a review posted for that?
We do, yes, sir. Yeah, I do have the review posted, and it's there for download. Okay. All right. Questions I can answer about induction before we finish up, guys? Okay. Let me give you guys back your assignments from last time. Okay. I will post the solutions, and if somebody will kindly email me to remind me to post that one problem, okay, I'll be happy to do that for you guys.